So this thing here is called a capacitor. It's a storage place for electrical energy, electrical potential energy. And a discharge capacitor doesn't have any energy in it. If I take this light bulb, hook it up, it's not going to do anything to the light bulb. No light. And what a capacitor consists of is two parallel metal plates. Typically these are rolled up, and in between them is some sort of insulator. What I've drawn here, we're assuming there's air insulating between them, but all sorts of things can be there. Mica, rubber, oil, something called an electrolyte, glass, a very toxic chemical called a polychlorinated biphenyl. There's lots of things that can go in there. And the job is to keep the charges separate. Although, as we've seen with lightning rods, you can get dielectric breakdown in any capacitor. And that's when you put too much charge, too strong an electric field, and you get a spark between the plates. So what do these two plates do? Well, let's hook up a battery. So I'm going to hook up the positive side of my battery to this plate and the negative side of my battery to this plate. And we'll talk about batteries quite a bit. They were invented in the 1790s by an Italian guy named Alessandro Volta. And basically, there's two chemical reactions going on simultaneously. The one at the positive end actually uses electrons up. So what happens is the electrons in here get used up, and electrons actually flow into the battery, and it starts taking electrons away from this plate. That makes this plate positive. Now, how does that work without charging up the battery? At the exact same time, there's another coupled chemical reaction going on at the other end, which is producing electrons. So we get this plate at exactly the same time becoming negative. And at any given time, there's the same number of positives and negatives on the two plates. So let's do some work to store some energy in it. I have this little hand crank generator, which unlike a lot of generators puts out voltage like a battery, a positive on one side and a negative on the other. So let's hook this up, positive here, negative here, and we'll start putting some work into it. I'm going to put quite a bit in. So that was a lot of energy being output. And that energy is now stored in this. And it's going to be stored there until something makes an electrical connection across these leads and allows the negative charges that were stored up on this side to go back to the plate where now there's just positive charges. So let's do that. Let's hook up this light bulb. And we can see the energy is available to us. The bulb is going to slowly get dimmer though as I talk. And that's because there's going to be less and less charge separation. And eventually the light will go out. So again, this isn't a battery. There was no energy stored in this originally. It only stored the work I put in as I pulled negatives away from where they wanted to be and put them on a plate that already had too many. In other words, I caused a charge separation. The battery had chemical energy. There were some reactants that were consumed to make products, and that did work. and it moved electrons away from positives. That's where they want to be. There wasn't enough electrons here, and the battery took more away. And it forced those electrons near negatives, where they really didn't want to be. So it's kind of like the anti-Robin Hood. It stole from the electron poor and gave to the electron rich. And that stores energy. So that energy is now available for use, just like this textbook, what I looked at. I'm doing work on it, energy is being stored. It's available for later use. I think an easy way to understand the analogy with gravity is to compare a capacitor to a dam. So in this picture, I have an uncharged capacitor. Both plates are neutral. That's just like having a dam where the water on either side is the same. They have the same potential energy. This is not storing an energy difference that we could later use. But when you charge the capacitor, and when there's electrons in a place where there's too many electrons and there's not enough electrons in another place, that's just like you raise the water level on one side of the dam. You had to do work to do that, maybe through a pump. But now you've got an energy difference that's stored, and you can release that energy by letting this water fall back into that compartment. So right now, we're outputting 5 volts from the laboratory power supply. So I'm going to hook the capacitor up to that. So, charging our capacitor. And now we'll hook that charged capacitor back up to the generator. So, the capacitor can definitely be charged in a number of ways. It holds energy until we need it. And then any electric device can take that energy and use it. We're going to use this same 1 farad capacitor to demonstrate how capacitors behave in a DC circuit. So right now, I just have this light bulb hooked directly to 4.5 volts. So current is flowing out of the positive, through the bulb, and then back to the power source. What I want to do is hook our capacitor in the circuit so that we go through the capacitor and the light bulb. Let's see what happens in that case. So I've got our circuit all hooked up, ready to go. The positive lead of the power supply is hooked to the bulb. Current will flow through the bulb, through the capacitor, and then back to the supply. When we turn it on, current is indeed flowing, which we can see because the light bulb is lit. But if you look, over time the bulb dims, which indicates less and less current is going through it. And eventually it becomes invisible as current drops to a very low value and eventually approaches 0. So this is what happens when you charge a capacitor. At first it's almost like the capacitor is a bare wire. Current flows through the bulb as normal. But at the end, it's almost like the circuit is broken. The capacitor is like an open switch. So what's actually happening there is the negative side of the battery is donating electrons to the plate down here. The positive side of the battery is stealing electrons from the plate up here. So electrons are flowing in a loop like this, which means conventional current is flowing like this. And when the circuit is first applied, as far as the bulb's concerned, current's flowing through it. But eventually the plate gets charged and everything up here is at the same potential, positive 4.5 volts. Everything down here is at the same potential, 0 volts, so current ceases to flow. The capacitor is charged, however, and we can get the energy out of it if we totally disconnect the power supply. And then we hook the capacitor up to the bulb. We'll get that energy until the capacitor completely discharges. So a capacitor is a way of storing electrical energy, and that can be used in various places in a circuit to take away electricity when it's not needed and to give it back when it is needed. I don't know the last time you used one of these, but it's a disposable camera, not digital, it uses film. And if we want to have enough light in dim situations, we have this flash. And what you would basically do, this one's already been used, you would flick this switch on, you would advance the film, and you hear a whining. And eventually, after a while, this light would start flickering orange. And that would mean the flash was armed. So let's bust this open and see exactly what's in it to make the flash go. My cat is trying to help, and she's not being too helpful. Alright, so here's the camera busted open, and here's a fresh one. There's the film with the pictures. I'm not sure what they are, so I should probably develop those. But the business end of making the flashlight is this. It's a single AAA battery like you'd have inside a graphing calculator. And that's not going to make a bulb light very brightly. The bulbs you saw in the other part of this video have 4.5 volts across them. That would be 3 of these. It's only 1.5. So how does something that can't generate that much power make an incredibly bright flash? Well, the trick is hiding behind the flash is this capacitor. So looks a lot like the one you saw already. And that battery didn't provide a quick enough flow of electrons to make the flash work. It would be like going up to a big water wheel at some huge industrial plant with a garden hose and just aiming at it and spraying it. So the thing's not going to move. So how do you make a battery power a flash, which needs to have tons of electrons flowing through it all at once? You wait. Just like we could take that garden hose, and instead of pointing at the water wheel, we could fill up a dam, fill up a lake behind a dam. Eventually we'd have so much water there that when we opened up the floodgates, whoosh, it would definitely turn that wheel. That's what we did here. Battery charges up the capacitor. We have the flash bulb, which I'm going to model here as a light bulb. This gets hooked up to the negative plate. The shutter on the camera is hooked up to a switch. And when you want to take your picture, that switch closes. And a whole bunch of electrons all at once, whoosh, go back to where they want to be. It discharges the capacitor. And because that happens so quickly, just like when a dam fails and all the water rushes out, you get a lot of energy all at once, and that's why you get the bright flash. Another place capacitors are essential is in the process of converting the electricity coming out of the wall, which is called alternating current, into the electricity that a battery can use, which is called direct current. In a battery, if you measure the voltage as time passes, it stays approximately constant. Electricity always flows in one direction as it's going through a circuit like this, so we call it direct current. But the electricity coming out of your wall is different. In the United States, one of the pins in your wall has a potential of 0 volts, but the other switches back and forth between positive and negative voltages 60 times every second. There's a lot of reasons for this, which we'll talk about later on. But a device like a phone has to be able to take electricity like this, a phone charger, and turn it into electricity like that. A capacitor is essential for that. As you go through the process of converting this electricity into this, at one point you get this bumpy curve where you've got electricity that's in peaks with really sharp valleys between them. What the capacitor does is when you're in one of the peaks, it takes some of the flow of electricity and it stores that charge. And then when you get to the valley, it releases that charge. And that smooths out, you can see this little green line, the signal that's coming through the capacitor. If you think of a dam up the river, historically before it was there, maybe there's too much rain, and the rain just floods the river and washes everything away. But if you've got a dam, you can trap the excess water behind the dam, and you can release it more reasonably. This can also help prevent droughts, because all the water you store up when you have too much, you can release when you don't have enough. We use capacitors in the same way in alternating current circuits. Just one thing to note, capacitors charge up when you're using a device, and that energy is stored there for a long time, sometimes a very long time, like years possibly. It's very important that you are very, very careful when you take apart electronics, that if it says warning shock hazard, you take that really seriously, because there may be a lethal charge lurking in capacitors, even a device that hasn't been on for a very long time. If you accidentally touch the wrong thing, you can get a pretty good zap. Now, this energy that I've stored in here is not going to be enough to hurt anybody, but the energy stored in some capacitors can be. So just because a device is unplugged doesn't mean it can't hurt you, even if it's been unplugged for a very long time.